Let's solve problem 1.39 from Microelectronic Circuits 8th edition by Sedra and Smith. Give the binary representation of the following decimal numbers. So you recall that decimal is base 10, binary is base 2. So that's essentially what we're doing here. Now, whenever I convert from decimal to binary, I always start by making a table where the left column is I and the right column is 2 to the power of I. What we're going to start doing is incrementing I, starting from 0, and then just incrementing by 1. And then we'll write the corresponding value to the right. So if I is 0, 2 to the power of 0 is 1. If I is 1, 2 to the power of 1 is 2. If I is 2, 2 to the power of 2 is 4. And we're going to keep doing this until we reach or surpass the maximum number that we're trying to convert, which is 63. So let's do this. I believe it'll end up being 6 times. So if I is 3, 2 to the power of 3 is 8. 2 to the power of 4 is 16. 2 to the power of 5 is 32. And 2 to the power of 6 is 64. We have now passed 63, so we're ready to actually start converting. I'm going to start with 5. So what we do, or what I do usually, is I'll write 5 and I'm going to write I equals below it. And the way this is going to work is we want to subtract the largest possible number from 5 from this 2 to the I column without making 5 negative. And we're going to repeat this until we get to 0. So the largest possible number I can subtract from 5 without becoming negative is 4, which equals 1. And below this 4, I'm going to record the corresponding value of I, which is 2. So the next number I will subtract is 1. It's the only number I can subtract now, and we'll get to 0. And for 1, I equals 0. Now, we're going to actually write the binary representation. So we go from right, starting at I equals 0, and we're going to increment to the left. And essentially, if we have a recorded value of I, then above that we're going to write a 1. All other numbers will be 0. And we can also delete any leading zeros from our number. So 5 in binary is 101. And to help kind of understand how this converts back, if I wanted to go from decimal to binary, this would be 2 to the power of 0 plus 2 to the power of 2, which is 1 plus 4, which is equal to 5. That's what that binary representation is telling us. So let's continue with 13. So the greatest possible number we can subtract is 8. That gets us 5 for I equals 3. The next largest number will be 4 for I equals 2. That equals 1. Then the last number will be 1 for I equals 0. So our largest value of I is 3. So we're going to go 0, 1, 2, 3. Make a little placeholder for those. And we have I at 3, 2, and 0, which makes 1. We'll put a 0 for our place of 1. So 13 in binary is 1101. Now let's do 32. So we can just immediately subtract 32 to get 0 for I equals 5. So we need to go up to 5, so we're going to write 5, 4, 3, 2, 1, 0. We have an I at 5, so we'll write a 1 there, and that's it. So the rest will just be zeros. So that means that 32 in binary is 100, 000. 32, not 33. Okay, now we'll do 63. So the largest possible number we can subtract is 32. That gets us 31. For I at 5, next biggest number will be 16. That equals 15. And I is 4. The next biggest number is 8, which gives us 7. And I equals 3. Next biggest number is 4. It equals 3. And I will be 2. Next biggest number is 2. That equals 1. And I will be 1. And lastly, we subtract 1. And I equals 0. So again, the biggest value of I will be 5. So we go 5, 4, 3, 2, 1, 0. Get my placeholders. So we can see we have an I at 5, 4, 3, 2, 1, and 0. So that means 63 in binary is 1, 1, 1, 1, 1, 1. And then lastly, 0 is just 0 in binary. So hopefully you're able to kind of see the methodology that I use.